Hey everybody! Today I'm going to talk about large language models and the future of AI, or what I learned building a really big model. My name is Connor. You can find me at MP Collapse on Twitter and other symptoms of the inevitable decay of our society. I am most well known for being one of the co-founders of EleutherAI. We call ourselves a loose research collective, aka glorified discourse server, interested in scaling, alignment, and open sourcing ML research. So of course there's a joke about the Discord server part, but if anyone knows, we do think we are the Discord server with the most publications. If anyone has any other info on other Discord servers publishing, we'd love to compare. But yeah, we are most well known for our ongoing efforts to build a open GPT-3-like model. We don't call it replication. It's not technically replication because there's some details of the GPT-3 model that we can't know for sure. And there's also some improvements that we've made to these models since then. And I'm going to talk a little bit more about why we think it's important and so on in the future. And basically, I'm here today because I want to tell you a story of three GPTs. So there's been a lot of hype, there's been a lot of anti-hype around these GPT models. GPT-3 in particular has, dominating a lot of headlines. There's a lot of people that say it's overhyped. There's a lot of people that have a huge hype for these models. And I want to talk to you a little bit about why I think these models are very important and what they tell us about the future of the field and how they change the paradigm of how we do AI. But before we get too into the weeds, I first want to just establish, for those who don't know, what are the GPT models. So the GPT family of models are a family of models built by the company OpenAI, and they are outer regressive language models. So what that means is they are trained on huge dumps of internet text, forums, Wikipedia articles, chat rooms, whatever, to predict the next word. So if it saw a fragment of a sentence like pears are, it might then continue that sentence with green or delicious or whatever else it thinks is the most likely continuation of that sentence. These what I just showed is what's called a prompt. So pairs are is the prompt, and this is the main way we interact with these models. We give them a prompt, and we let the model auto complete, continue writing from our prompt. One more term just to explain for those who are not super familiar with how these models work. So these are neural network models. And the way you can kind of imagine a neural network is a big box with millions and billions of knobs on it that you can twiddle. And these are called parameters. These are individual numbers that you can twiddle. And to build a good neural network, what you want to achieve is basically to twiddle all these knobs until you have a good configuration that makes the box do what you want it to do. So you can kind of imagine that the knowledge or the skills or the algorithm that this box implements is kind of encoded in these parameters. And that's going to be very important in just a bit here. So GPT-2 was already pretty impressive. No one really talks about GPT-1, but it was also interesting for its time. But GPT-2 was kind of when people tend to have first heard about these kinds of models. It was really good at generating some like vaguely plausible news stories, some, fun fiction, usually just in the order of paragraphs or whatever. But then with GPT-3, we saw a really big advancement. So GPT-3 really is very good at generating very convincing text of all kinds. It can write blog posts, it can, Wikipedia articles, you can use it as a chat bot. It can really generate a lot of it. A lot of it is really very good. So you might be thinking, well, this GPT-3 must have been a great scientific advancement. They must have found some, huge theoretical breakthrough in natural language processing to be able to, get from GPT-2 to GPT-3. But, well, the punchline is that GPT-2 and GPT-3 are the same thing. They have the same architecture, they're trained by the same method, just that GPT-3 is about 100 times larger in size. It's a much larger model trained on more text and with a much scaled up model. Far more parameters, far more computing power is put into GPT-3 compared to GPT-2. And so nowadays it's like more and more becoming accepted that that this makes sense. Yeah, bigger model performs better, but this actually goes against a lot of what people thought pre GPT-2 and GPT-3. I remember, so like before GPT-2 came out, it was already the case that people thought, oh, deep learning not really scaling well. It's so sample inefficient. It takes so much data, whatever. It's not going to scale. And GPT-2 came out, and people were like, oh, this is ridiculous. This is the absolute limit what is possible. I remember when the BERT paper first came out. So BERT is like a model kind of similar to GPT. They were almost apologetic in the paper for saying that they have such a huge unwieldy model with 300 million parameters. I don't remember the last time I used the 300 million parameter model except for debugging. Times change quickly. So then with GPT-3, we hit the, the logical extreme of 175 billion parameters. That's massive. That's unbelievably huge. That doesn't fit on any GPU. Yeah, it's a massive hassle to deal with a model of this size. But OpenAI pulled it off, and they showed that the models perform better. And I'm not just talking about benchmarks here. It does perform better in benchmarks. That is definitely the case. But I really think that relying solely on these benchmarks is kind of missing the forest for the trees when it comes to these kinds of models. Really, the difference in using these models is qualitatively so extremely different. So to give you an example, a good friend of mine is working on a GPT-powered video game called Project Electric Sheep. Check it out. And one of the things he wanted the model to do was to generate names for characters in the game. So GPT-2, this was a real hassle. You had to give it lots of examples and run it multiple times and check that it stayed on topic and didn't start talking about something different or whatever. It was a huge hassle. But with GPT-3, you could just kind of ask it. I don't know how any other way to put this. It was just kind of astounding. It's just you could just write, "This is a video game about X. Here is a list of characters in this game." And it would just pretty damn reliably output a pretty good list of names for your game. Not every time, not 100% accuracy or something, but way more than good enough to be used for this application. And this is kind of amazing. This thing was just trained to just predict random internet text. It was never trained to come up with cool names or to understand this. What are the chances that it would have seen this kind of prompt in its text? I mean, it wouldn't have, because we created this prompt and it comes up with new names every time, and sometimes really clever names too. It's kind of so. The really interesting thing here is that it's not as interesting that it fails sometimes. Sure, it fails some of the time. It's not 100% reliable. But what's amazing is that this works at all, ever. That's really a fascinating thing. So in the original GPT-3 paper, I actually think that GPT-3 is the second most interesting thing. I think the most interesting thing about the original GPT-3 paper and some follow-up papers is the scaling laws that we have found for performance. So one way I use to explain what scaling laws mean is this meme here, where in classical learning we have we have to be careful about the bias variance trade-off and use an unbiased estimation kernel, and we have to make sure that our heuristics are well crafted. While in neural networks you have to stack more layers, lol. And this is obviously a joke, but it's also kind of not. So in these really amazing, really rather shocking graphs, what we see here on the y-axis is the performance of the models. Lower is better. And on the x-axis, we see various parameters that can be varied. And the first one here, what we see is each blue line is the training lines over the loss of the model over time of successively larger models. And what we can see here is that as we have more compute and we train larger and larger models, we find this pretty consistent power law that will predict the final performance we will see from these models given the amount of compute we have available. We see similar laws for dataset size and parameters. As we increase these parameters and increase the others in tandem, we can have a very accurate prediction of what loss we will end up with. This is pretty amazing. I found this really rather surprising that this was not at all obvious at the time. And I still, to this day, I think people do not realize how fascinating this is, that you have these, and just purely empirical, there's some attempt at theoretical explanation, but ultimately empirical, that, observation that as we have bigger models and we give them more compute, they just keep getting better. This also leads to this rather surprising graph here, where what we see here is as we have a certain amount of compute. So we have a certain amount of GPUs that we run for a certain amount of time. What is the best way to spend that compute? You can spend compute in three ways. You can train your model on more data. You could train on the same data multiple times, or you can make your model larger. And so a common criticism of deep learning techniques is that they're so incredibly sample inefficient. Is that, to train a really large model, we need so much data that, that more than exists in the entire universe. And such. But what we saw from these empirical observations and large models is that yes, large models do need more data, but the most efficient way to reach a lower loss as you get access to more compute, it's more efficient to train larger models on comparatively less data. This means that as models become bigger, they actually become more sample efficient. This is kind of crazy. Like, I remember when I was taught neural networks, back in the day, I was still taught that, you have to be very careful to use the smallest model possible so that it doesn't overfit your data. But that just seems to be wrong, at least for these kinds of, very general tasks. For very small data sets that are easy to overfit, that might be different. But at least for these kinds of tasks, which are an interesting class of tasks, it seems that bigger really is better. Just keep making the model bigger. This also very much matches my empirical observations, is that if you just deal with large models, it's just easy. Like, been this paper from OpenAI, the Palms paper, where they fine-tuned the large GPT-3 model on, I think it was like 80 kilobytes of text. So like a tiny minuscule amount, and just updating on that once, the model learned incredibly well everything that was in that data. You don't need multiple epochs. It just learns things so much more efficiently as the models get larger. So a good friend of mine, Leo Gao, put this pretty elegantly in his blog. The thing about GPT-3 that makes it so important is that it provides evidence that as long as we keep increasing the model size, we can keep driving down the loss, possibly right up until it hits the Shannon entropy of text. No need for clever architectures or complex handcrafted heuristics. Just by scaling it up, we can get a better language model, and a better language model entails a better world model. This really hits it on the head why I think the scaling laws are the more interesting part of the GPT-3 paper. Because I remember as back in the day, and still to this day, many people still, very much believe that we need fundamental algorithmic breakthroughs to make progress on these various tasks. Is that, we've hit a limit on what our methods can do or whatever. But the scaling law shows that at least empirically, that seems to just not be the case. I'm not saying that these scaling laws might not hit a wall eventually. They definitely will when they hit the Shannon entropy, but we don't know when they will hit such limits, how fast it would go. If they hit Shannon entropy, that means they perfectly predict everything as well as possible. So they're already a perfect method and know everything there is to know. We don't know how far how close our methods can get to this, because so far we don't have line of sight to any, curling of the laws. So far, if we had more computing power, we would predict that models would just continue to get better. No new insights needed, just more computing power, which is kind of, it's kind of weird. And it goes very much against a lot of the intuitions that a lot of people in this field have. That's why it feels like a kind of a new paradigm. Even in academia, I feel that most academics still haven't grokked like how big of a deal scaling laws are and how much this tells us about how this, how the field will progress probably in the future. And you thought this only worked for language? Surprise! It also works for other things. Images, text to image, video, math. Here from a follow-up paper here, we can see that you find scaling laws in all of these different tasks. As you just make bigger models and you just put in more compute, you get a better model with very predictable levels of performance. This is crazy. This is astounding. To me, this is a fascinating empirical scientific discovery. I did not predict this. I did not predict that there would be these scaling laws, that we could just, see a power law of performance for all of these very different tasks. But here we are. And I think this is something that is worth exploring. What does this mean? What can we derive from this? How far can these scaling laws really take us? The other half of the other side of this coin, of this new paradigm that we're talking on, not just on these how scaling up models, makes models that just fundamentally work better in very powerful ways. We also have this new, very strange way of interacting with these models. The prompt programming is the idea that, it's like finding the best prompt to get your model to do a specific task. It's, writing in a specific style, summarizing a text, translating, whatever. A lot of people here now are quite familiar with this. Like we've come used to yes, this is the way you interact with GPT. But can we just take a moment to pause and think about how crazy this is? Think about the traditional way we do ML. We define a very clear objective. There's these many classes, and we do softmax over the logits or whatever, or it has a very specific action output space or whatever. We have a very, very specific way of interacting with our models. But here we're just kind of talking to our models. This is wild. I don't know why people aren't freaking out more about this. It's kind of amazing how we literally build a model you can literally talk to, and people are like, but it's not very good at math. Imagine in a sci-fi story, the guy in the lab invents an AI you can talk to. That's usually the point in the story where shit starts getting real. And it's not exactly talking, of course not. It's weirder than that, which is to be expected. It's not a human you're interacting with here. It's like a weird AI simulator something system. I don't think we really know what these things are. And one of my favorite examples of just how weird this interactions with these kinds of systems can be. So is that often just by telling GPT-3 to be better works. So my favorite example is a paper that some friends of mine wrote. And they showed that, so in the original GPT-3 paper, the way they evaluated the translation performance of GPT-3 was they wrote a prompt kind of like English, English sentence, French, autocomplete. And my friends showed they could get significantly better performance, so multiple percentage points, non-trivial improvement, by instead using a prompt that looked like the English sentence is translated by the masterful French translator as autocomplete. And the masterful was really important. If you left out the word masterful, then performance would drop. Very often, by just telling GPT, you are super smart and never make any mistakes, its performance improves, which is just wild. Who would have predicted that ahead of time? With hindsight, it kind of makes sense. I can see why this happens, because ultimately, what GPT is trained on is to simulate its text, is to replicate this text that it's trained on. So in a way, it's simulating a median internet user. So in a way, it will also have circuits to simulate errors. A very fascinating thing with GPT is GPT-3 is pretty bad at math. There's several reasons for that. But one very fascinating thing is that when GPT-3 makes errors in math, it makes very human errors. It forgets to carry a 1, for example, and stuff like that, which is not the kind of error a computer would do. In a way, it has seen humans, fail to carry a 1, and now has circuits to simulate making that mistake. And by telling the model, you are super smart and don't make any mistakes or whatever, you are telling it to use circuits that simulate not the median internet user, but someone who's really good at the task you're trying to do. Which of course doesn't mean it will do it perfectly, it's an imperfect model. But the fact there is a very measurable difference between these things is kind of wild. And as these model size increases, this becomes easier and easier to do. This is the one thing that people that if they use GPT-2 and 3 will always tell you, is that the biggest difference when using GPT-3 is that GPT-3 just kind of gets it. With GPT-2, you have to be really careful how you phrase things, and it'll often go off topic, and it's hard to keep it on track for a long period of time. GPT-3, often even if you don't perfectly explain what you want, or you say it very natural language, often GPT-3 will get what you mean. Not always, not 100%. But again, the interesting thing here is not how often, that it doesn't work all the time. The interesting thing is that this works at all, ever. We can also see this quite a bit in this graph from the original paper. So what we see here is the fuchsia paradigm, which is what happens if you give the model multiple examples of what you're trying to do in the prompt. So for example, if you're trying to get the model to solve a math problem, you might give it a few examples of math problems that are already solved to kind of give it the hint of what you want to. So the green line at the bottom of this graph is GPT-2. And as you can see, it really doesn't know what's going on. And, even giving it a good prompt doesn't really make that big of a difference for its performance. But if you look at the blue line, which is the maximum size GPT-3, even giving it a single example of what you want it to do jumps its performance from around 10% to almost 50%. That's huge. So in a way, these models know a lot of things. You just have to know how to ask it. You have to know how to prompt it to get that higher performance out of these models, which is just kind of weird. This is not how old, ML, the previous paradigm ML models worked at all. If you have an ImageNet training model, and you put an image in it, you get a class out of it. That's it. There's no other fuckery going on. But with these models, your choice of prompt can really make a huge difference to the final performance of these models. As a Gwern, who's done a lot of work with GPT-3, says it, is that the given performance on a given prompt is the lower limit on what the model might be capable of. We've also seen this with this graph. So this is from a different paper. So we see on the blue line here is the performance using a human made prompt. And as the model gets larger, it gets better. But what we see here is the orange line is the performance if we fine tune our model directly on the task we're trying to do, which gets quite good performance out of it. And then this green line here is a specific technique where we basically use backprop to algorithmically generate prompts. And as you can see here, there is a huge delta between the performance of the green line and the blue line, which means if we only evaluate our model using blue human-generated prompts, we're not actually getting the best performance out of our model. The model's actually capable of far more than that. We just aren't asking it the right question. We aren't getting out the right performance. A fun way I like to explain what to say is large language models are like alien artifacts that fell from the sky one day, and we're still banging rocks against them trying to make them do something useful. I think we haven't yet figured out what the correct way is going to be to interface, to control with these kinds of models. We're still in such a primitive stage that I think we really do not understand what these models are capable of and what we can possibly do with them. We're really in the early stages. To me, large models feel like one of the first real examples of a true 21st century technology. Like a lot of the technology around us is just refinements of 20th century technology. But to me, these large models seem to be like fundamentally a 21st century technology. Something so new, something so radical that we need a whole new paradigm to think about how to use these things, how to control these things, how to build, products and applications and whatever around these kinds of things, which is why I'm so excited about them. So here's some key takeaways from the scaling laws. So scaling these transformer type models, GPT type models, shows smooth scaling laws to performance with no obvious limits in the site. Not saying that there are no limits. I'm sure there are some limits somewhere, but so far we have not seen them. This is just an empirical observation. The current models are still infrahuman for many tasks, but we can't be sure since prompt programming seems so highly suboptimal. This is what I mean, is like, yes, GB3 is not the best model at literally everything. It's not really the best at almost anything. Like if you make a custom made model for translation, of course that model is going to be better at translation than GPT is, and so on. But of course it's not human performance for many, many things. But often something I see people do is that they'll write one prompt asking GPT some question or to do some task. The model fails and they say, ha, look, GPT can't do this task. But then someone else a while later comes along, writes a slightly cleverer prompt, and suddenly the model can do exactly what it was asked for. So it's really hard to know what these models are actually capable of. I think GPT-3 may well be much smarter than we think it is. It's a very intelligent system emulating a media internet user. Sometimes, as funny as it is, if your model gives you bad performance because you gave it a dumb prompt, it may just literally be trolling you because it's probably been trained on trolling. So if you give it a prompt that makes it troll you, it will probably troll you. That's just an actual thing these actual models can do to actual researchers, which is just kind of weird. Kind of makes you think, doesn't it? So what does this mean for the future of AI? Well, many things. As I said, as I started with this whole talk, I feel like there's a whole new paradigm, a whole new way to think about AI and machine learning and how we interact with these systems. I really think that these large general purpose models will be the basis for many, many applications. Stanford likes to call these foundational models. Whether or not you like that term, I think it kind of captures the essence that these are foundations on which other things are built. You build products on top of GPT or on Clip or on whatever other foundational big models might be built in the future, and then and then turn to produce all kinds of interesting things. Like with GPT-3, you can make a chatbot, or you can make a video game, you can make a copywriter, you can make all these different things by using this basis model and then like building on top of it. I think this is going to be a common paradigm. It already is a common paradigm. The how often are NLP tasks nowadays solved by taking a BERT model or a GPT model or whatever and fine tuning or integrating into a pipeline. This is already very common. I think this is going to just become more and more common. Unfortunately, training these models will become increasingly expensive and inaccessible. I don't like this. I endorse this. This is just a matter of fact. Is that if scaling laws continue to hold, and whoever has the most compute can make the best model, whoever has the most compute is going to have the most model. And that's going to be the person with the most money. I think in a way we are entering an era of high energy ML. So we computer scientists have been very spoiled for a very long time, that we are used to having, just like a PhD student with a laptop being able to sit down and work on the most cutting edge part of any field. And this has been the case in most other scientific disciplines for a very long time. If you're a particle physicist or a biologist or a chemist or something, you need access to extremely expensive hardware, like particle accelerators and wet labs and stuff, if you want to do the most cutting edge work in your field. And I think this is coming from ML, at least to a certain degree. There always will be low energy ML as well, and that will be a very valuable field of research. But I think there is going to more and more be this field of let's do certain types of very cutting edge work. You will need access to particles accelerator scale infrastructure. You will need access to huge supercomputers to be able to do this kind of work. I hope that at some point, academia and nation states are going to pick up the slack here and fund this kind of stuff the same way they currently fund like particle accelerators, but we'll see about that. I think there's a likely future business model that we also are now kind of already seeing starting to emerge, where very large corporations will rent out large models as the basis for other products. We're already seeing the prototypical example of this with OpenAI's API, where they've got this big company building this very large model, which is very expensive, and then they rent out access to like startups and smaller companies who then build products on top of this foundational model. I see this becoming more common, that in the future we're going to have all kinds of these like big foundational models for text and for speech and for video and for all these kinds of different things. And the models themselves will be general purpose. And then, startups or other companies will rent access to these models or buy access to these models to then build other products on top of. It seems like a pretty likely business model to become more relevant in the future. This is, of course, unfortunate for many reasons, and is a big part of why EleutherAI exists. So there's been this little project that me and some friends have been doing for about a year now. You may have heard of it, EleutherAI. And one of the things we're very interested in doing, of course, is building very large models and making them accessible, releasing them open source for researchers all across the world. And because we believe that these models will be important for the short, medium, and maybe even the long-term future. We think AI is, an incredibly powerful technology, and that if these scaling laws continue to hold, these technologies may well scale to truly amazing power. And so we think it's really important to be able to study and understand these kinds of models. I've written a blog post where if you want a more philosophical treatise about why I think it makes sense for us to build and then release these kinds of models. Basically, there's kind of two sides to this. On the one hand, of course, it's important to help people utilize and benefit from this powerful new technology. It would be a real shame if like one of the first real 21st century technologies was exclusively in the hands of a few, North American mega corporations. Feels like a big shame. But on the other hand, also, what I think is actually, and hopefully academia will pick up some slack here, but it's not quite there yet. But even more important, in my opinion, the corporations have incentives to downplay the weaknesses and risks of these technologies. This is just how business is done. These are extremely expensive things to build, and they have an incentive to want to make, to make back their investment. It's just how the game is played. It's just how business works. And this can be a real problem because these are very powerful technologies, and I expect them to only become more powerful. And so it's very important to have, I think, one of the main reasons we do what we do at Eleuther is to make it accessible to academics, to hackers, to take apart this technology, to interrogate this technology, to understand how this technology works, where it fails, where it can be dangerous, where it can be improved on, where, how to better integrate this into productive use. One of my best possible outcomes of EleutherAI is that I imagine in the future, kind of like in the 90s when there was the emerging scene of the software hackers. We had corporations who were jealously hoarding their software and pretending there were no bugs and refusing to patch things. And then emerged this scene of hackers that took apart this software and saw the flaws in the software and lobbied to make the software more secure. And I hope the same happens, that there will be a emerging generation of AI hackers that will take apart the software and push to make the software actually safe and beneficial for the world. Because ultimately, we can't stop this technology from coming. We need to do our best to understand and to control it. I really think that AI has the potential to be one of, if not the most powerful technology humans have ever invented. It has the potential to do unimaginable amounts of good and improve the lives of billions of people. But like every powerful technology, whether or not it's the best thing to ever happen to us or the worst thing will depend on whether we learn to wield it responsibly. Thank you.